So, hello everybody. I know it has been some time before this practical exercise become available. However, I wanted it to be as clear and concise for you as possible. Although, make no mistake, the task we are going to achieve here is not so simple and time consuming as well. Luckily for you, I have already prepared a template of the code, some function you may use, so you don't really have to worry about trying to implement the Viterbi algorithm that we have been studying in previous practical exercise by yourself. And you can use the function I have provided. So for this practical exercise, we are going to need the main script template, which is optional, of course. You always are welcome to write your own program if you can. And Viterbi detection function, equalization function, which I have prepared for you. Now, if you have MATLAB, you may use MLSE EQ built-in, not really built-in, but some of toolbox functions, which does the same thing and it does it faster and maybe even more accurately. However, I realize that MATLAB is a commercial product with a high cost, so it may not be available for you. So I have tried my best to create an equivalent of such a function, which is possible to run in Octave or any other similar to MATLAB code. Of course, it will run in MATLAB as well, so you don't have to worry. But in MATLAB there is really a better alternative, which I will show you once we get there. So if you don't have MATLAB or communications toolbox in MATLAB, you really need this function to achieve this practical exercise. And this is actually what took me the most time to prepare, to debug, find all the problems, issues, and so you can now use it as you want. There will be a separate short video explaining how this function is organized and how it is programmatically achieving what has been done in practical exercise 5, which was, 6, which was previously, yes. So, if you have interest to understand better how this function works, you are welcome to study this additional short video. If you are not really interested in this, it's fine. It's enough for this practical exercise video to actually achieve whatever is working, and maybe you don't really need to know all the programming specifics and details of this Viterbi algorithm, how it can be achieved. So we are going to need this function. So let's read the tasks which we need to achieve. So the task number 1, which is general task, is to complete the code in template and so that it performs the tasks listed below. Yes, so our real tasks now would be to perform a simulation of CAM16 modulation type, which is what we did multiple times already, in channel with impulse response, which is the same as before for each of you, and additive white Gaussian noise for specific range of signal to noise ratios from 10 dB to 20 dB with a step of 0.5 dB. So we are interested to get a bit error rate plots, yes, depending on the scenario for each of 3 equalizing methods that we have studied. Well, DFE equalizer, the decision feedback equalizer, will be explained in the second part of this practical exercise video, and for the Viterbi and minimum square error equalizers, we already had this material previously. Yes, so this first part will be focused on these 2 types, and the second part will provide additional lecture insight as well as implementation in this program. So we will do that in one short video. So we need to run this simulation and receive this noisy and distorted signal from the channel and try to read it as best as we can. And our task is to find out which of these algorithms, well, obviously Viterbi algorithm should show the best results. However, we also want to know at what cost that happens. So Viterbi algorithm is one of the few methods we can use that actually can improve the situation to almost eradicating any problems with the channel. Yes, as you will see in this practical exercise, we will be able to get a completely restored signal, which otherwise by these two types of equalizers wouldn't be achievable. Yes, however, that comes often at a cost, so we will study what cost is that. Yes, so we want to plot all this bit error, so BER curves for specified SNR range for all three equalizer types, and the number of simulated symbols for transmission should be no less than 100,000. It is an adequate amount for this simulation, especially considering that we have 4 times as much bits, so that would be almost 500,000 of bits for transmission, and the signal to noise ratio isn't that um, really high, yes, for this modulation type to get some results. Of course, for 20 decibel probably we will not be able to adequately evaluate bit error ratio, especially for Viterbi algorithm, but it's not that important and it's not really worth it to spend so much time to run the simulation for days to have this big number. So okay, in addition to that, we are going to plot the ideal CAM16 bit error rate curve in perfect channel with noise, yes, to see, well, how good is each of these equalizers at solving its task. Yes. Finally, you need to include in practical exercise report the list of all tasks, of course the picture we are going to basically get in this practical exercise, which is basically final result, yes, with just one picture or maybe two pictures, I'm not really sure how it's better for you to organize. Of course, a conclusion, what you think about this, and as an appendix, a code including all the functions used. Just add them in the end because the code is getting bigger and bigger with each practical exercise, so it's more convenient to study it in the final part of the practical exercise. If you have some problems, if some results are not really correct or whatever, the code would help me to find whatever the issue might be. Yes, as before, you will be able to upload them. I just haven't added link yet, but there will be the same link here, which will allow you to upload your practical exercise number 7. So, with all that in mind, let's get to the practical exercise 7 template, yes, and see what do we need in the first part of this practical exercise. So for the first part of this practical exercise, we are going to need the template itself, which is somewhat filled in, as you can see, but the most parts you will need to program by yourself to actually make this working. This has been just arranged for you for convenience, so that it maybe not necessarily require too much effort from you to put to this practical exercise, as a lot of work will happen in the additional functions, yes, which you will load to this template. And these functions, however, you will have to work on yourself with all except, of course, Viterbi function. The Viterbi function for you is provided and you can use it. It has a lot of commands and additional video, as I said, for you to study better how it works, yes. So this function you don't need to change anything, so I'm going to close it. In addition, the task states that we need to simulate also MSE equalizer, which we already did, and we use two methods, yes, iterations method and correlation method. So you may choose whichever you like the most. So I have chosen iteration method 2, yes, in the practical exercise 4. Now here you can see the impulse response is different, but it's okay. We are going to strip some parts of this practical exercise, particularly this part of calculating the equalizer, and organize it as our own new function. So we are going to need that here for MSE equalizer part to actually find the coefficients of our filter, of our equalizer. Yes, and finally we will also need to perform a demodulation for CAM16, which we also did multiple times already. I believe 3 practical exercises used this type of function, so we are not going to repeat it once more. Just make sure that the output of this practical exercise is in the form of a vector column, which we achieve by performing these indexing operations. Sometimes we use transpose at the end here, sometimes we didn't. In this practical exercise, I, however, will not use any transpose and will expect this bin receipt vector to be the column vector. Yes, so that is something you need to pay attention. Otherwise, we don't need this function anymore as well. Just make sure it is copied to the same directory where is your template, yes, as well as Viterbi detect function, and we are going to make a new function which we are going to need, which is called, well, you can name it whatever you may like, yes, I will call it MSE eq function, yes, and this function is going to return the equalizer coefficients h of the impulse response h equalized, yes, based on the input data that we have received from channel with noise and all the distortions. Additionally, we need to know the true real data to actually find a correlation and better equalization technique. So basically this is a training process, yes. So we need to know the correct answers. In practice we usually use some training sequence before we send our real data, yes, and this training sequence can be used to achieve this task. Finally, we need to know the equalizers impulse response length, as we have tried different values here, as you may remember, 45, 15 or other values, yes, so probably we'll choose the best we have tried, yes, and finally the impulse response that is going to be needed. We'll return to this function later, yes, right now we have it prepared its empty file where we will put everything we need. But before we get to that function, let us start working on this program and completing all that we need. So during the testing and debugging, I would recommend setting this number of transmitted symbols to 1 power of 4. Yes, not 5, not 6, because it will take some time to run, especially in Octave, which is slower than MATLAB. But if something works incorrectly, you will have to wait too much time just to find out that you need to change something, run it again, change something, run it again, and so on and so on. So to make these runs as short as possible, maybe you even might consider using power of 3. Yes, well, I am pretty sure in my code, which I already have, of course, on the second screen, so I'm going to leave power of 4. And later on I'm going to show you the final results for the power of 6, how they would look differently. So what we have here specified is the number of quadrature amplitude modulation 16 symbols that we are going to simulate. So the base of the modulation, which is 16 number of symbols, and of course the size of the payload, for each symbol how many bits does one CAM16 symbol carry, which is 4 bits per one symbol, as you may already know. So now here we need to specify the channel impulse response. I'm going to use the same one as I used in the practical exercise 6, I believe, yes. So we are going to use this impulse response. Yes, I will show you alternative with another values just to see how it will affect results, because it does affect results. So each of you might get slightly or significantly different pictures than me, because you have different impulse response of the channel. Yes, that's main affecting factor itself, and you have it different. So now also we need to know how many samples this impulse response has. So we use command called length for this channel impulse response to find it out. Yes, because this L will be used in multiple places. Next thing we need to consider is the delay before we start reading the Viterbi algorithm symbols. Yes, so in a short video I explain this in more details. However, the basic idea is that, as you know, Viterbi algorithm branches, yes, and at some specific point right here all the branches merge into one single path. So the question is, how long should we wait before we start reading this path and be sure that it's actually correct one? Yes, so as you can see here, yes, uh, the good estimate would be 5 times per the number of states. Sorry, not number of states, but length of the impulse response minus 1. So constraint length is for coding with Viterbi algorithm. In our case, instead of constraint length, we have impulse response L. So L in my case is 3, yes, 3 minus 1 would be 2, and 5 times this number, that would be 10. In MATLAB code, you also need to specify this value. This is called a traceback length. In MATLAB, it's tblen parameter. Yes. So this is actually parameter that may affect our performance. If it's too small, you may get more errors than needed. If it's too big, you will simply have a long delay before your data is available. Yes, so it's quite important. We don't really need to use more than that. Well, actually, what would be even better is to program it, if in case you change your impulse response, to automatically match the new case. So I might, for example, add one more sample of impulse response, and then I would have to update this number to 15, which is not convenient. Yes, so let us better program this like this: L minus 1. This way, if you change impulse response, this delay will also change. We will now leave this for zeros. Well, maybe not even for zeros. I actually can copy this now, which is 45 for me. I am going to choose the best we have studied so far. Yes, and the delay is going to be a half, roughly a half, because this is an odd number. We need to decrease it by 1 and take the half of this decreased value. And this would be the delay of MSE equalizer. Yes, so each equalizer introduces some delay. Yes, be that Viterbi or MSE or whatever else. Now for DFE equalizer, we will also have to specify some parameters. However, we are not going to do that right now. Yes, we are going to do that in the second part of this practical exercise. So finally, we start generating our symbols in the same way as we did before in the previous practical exercise. So I'm going to briefly copy the parts of the code which you may find in previous practical exercises. Yes, this is the number of symbols, which is 16. We generate it as an integer from 1 to 16 in random way and use that as an index to address these complex symbols. Yes, so if symbol data is 1, then we will replace this 1 with this. If symbol data is 16, we will replace 16 with this. Yes, so we did already that multiple times. So we are going to do that by reading this map with these indexes right here. And since this map is a column vector, we may want to make it as a row vector if we want to display some results in console, because in raw way it will be more convenient and occupying less space. Yes, well, this is not really necessary, but I have decided I want to have my data in the format of raw, so you will need to stick to that in future in other places as well. So that is our data, modulated data at the input of the channel. Now what we want to know is how this channel is going to distort our data. So actually, as you can see, we did that the same way here. Yes, and the channel distorts data by using a command called filter. Yes, so I'm going to copy these with my particular impulse response h-chan, that is specified here, yes, for the data in the vector A. Now, this makes our data with inter-symbol interference distorted data, which needs to be equalized before we can demodulate it. So if we don't equalize, you have already seen that the errors are a lot of errors even without any noise, and if noise adds in, so the situation becomes only worse. Yes, so we will need to equalize the signal. However, previously we did equalization without any noise, and it achieved very good results. Will it be so if we add some noise? That is the question. Yes, so we want to study this now in this practical exercise. For the noise calculation, we need to evaluate the average energy of each transmitted symbol. That would be mean absolute value of the symbol at the channel output. Yes. So we evaluate the average energy not of these perfect symbols, but of these symbols that are actually produced by our channel. Yes. So that is important moment. That is the energy of one symbol. Since we want to know the bit error rate and we want to calculate the bit energy, we need to divide that by the number of bits so that we know how much power or energy in this particular case is carried by one bit. Finally, we need to transform our signal to noise ratio from logarithm scale in decibel into a linear scale in times. Yes, since SNR is a vector of multiple values, please make sure you actually use the dot power operator so that each of these values is going to be powered. Yes, not like I really want to power scalar 10 by the matrix SNR. Yes, we want each element of the SNR to be affected by this function. For this, you have to specify this dot. Finally, we express the noise power spectral density from this expression. Yes, which would be bit energy, which we have here, divided by all of these expression. Yes, and once again, since this is a vector, we need to use a dot. So this way we have calculated noise power spectral density matching for each signal to noise ratio depending on our signal of the channel. Since each of you have different impulse response, this will be different noise power. However, the relative ratio of signal power and noise power will be the same for each of you, which is this range from 10 to 20 decibel with a step of 0.5. Yes. So with all that in mind, we can now actually go to the simulation. The simulation is organized in this for loop that takes one SNR value, processes all these results, records the bit error rate, and repeats the process for the next signal to noise ratio. Yes. So there is some textual output to make it more clear. Yes. However, we are interested in generating the noise for our program. Again, we did that multiple times already. Yes, I believe it's somewhere here also available. No, not in this practical exercise. In this practical exercise we didn't have noise, but you may remember that what we need to do is to generate the random normal process for the real part, which is here, and for the imaginary part, which is here, with this one eye. Yes. Accordingly, that would produce the standard normal process with a deviation of 1 and mean 0. We need to multiply the standard deviation by our noise spectral power density half and the square root as usually, yes, both for real part and for the imaginary part. This way we would actually produce the noise of this power, which is our goal. Finally, what we want to do is to add this to the channel output signal to have the noisy version of the distorted signal. So first our signal is distorted by the channel, next we add some noise to this. And with all that in mind, what we want to do is to try and recover the perfect signal by using different equalization techniques. So first method would be the Viterbi algorithm that we want to try. Yes, and for this purpose we need to call the function Viterbi detect fun that I have provided for you. Yes, in brackets for this function, well, actually let us open it once more to see the parameters we need to specify for it. You should provide the channel impulse response, your sequence of symbols with noise that you want to recover, and the delay for the reading process. Yes, so these three parameters need to be specified. Make sure that you specify for the real part only the real part of the signal, and for the imaginary part accordingly the imaginary part of the signal. So we process them differently. Why, you may ask? Well, the answer is quite simple. So if in our particular case, right now in this practical exercise 7, my state diagram of the channel trellis would look like this. So we have a total of 16 different states, which is 4, that is if I use separately, yes, real part, which changes +3, +1, -1, -3, yes, and imaginary part separately. So in that case, my trellis would have 16 states. Yes, all the states can be mentioned here. The transitions are possible shown here. I have split that in 4 pictures just to avoid having one big overcrowded picture. Yes, but the idea is still the same. So that would be 4 different symbol values, +3, +1, -1, -3 at the power of L minus 1. L is 3, so that gives us 16. Now, what would change if we want to make a complex signal? Complex signal now has 16 possible states, yes, denoted accordingly by our constellation map here, 16 different symbols, and the same way it would produce L minus 1 power, that gives us square of 16, 256 states. Yes, so then we would have to produce a Viterbi trellis with 256 states, which would significantly make the process longer. Yes, so in our case it is better to have 2 Viterbi algorithms each for 16 states rather than one for 256. However, it is still possible, yes, to use a complex states. Yes, it's just not really worth it. Yes, it's more efficient to separate real part and imaginary part. So okay, we return to our practical exercise and do this for real part separately and for imaginary part separately. Once we have processed with Viterbi algorithm each of these parts, we are going to add them up together back in the complex signal. Yes, so real part plus imaginary part multiplied by complex unit, 1 imaginary unit, yes, 1i. Now we can apply our demodulation. Yes, so you need to realize that actually this function already at the final step includes this delay. So you are going to have delayed version of the signal, not full, and therefore during the error counting you will need to account for this delay too. But this received data is already delayed, so no need to introduce any additional delay here. What we want to do now is to simply demodulate that by using our CAM16 demod function, which was available in one of the previous practical exercises. Yes. So similarly, we need to now find out the not really L, by the way, but and delay Viterbi symbols +1. Yes. This is a small mistake in the command, which you need to be aware of. So okay, which we also did multiple times already, I believe here too. Yes, Let's check it. It was in the beginning. It was in the beginning. So the approach is to use a decimal to binary conversion, and then to check if the symbol matches the text symbol of 1. Yes, if it does, it produces logical matrix, which we then transpose and have this as a binary vector unwrapping into one long vector. So again, please pay attention to the previous practical exercises to see in more details how it was done. In this practical exercise, we are going to just reuse this approach once more. Yes. So that would be quite a long row. Let me actually move a little bit this. Now, for me, it is called n delay Viterbi. Yes. So I cut out the last n delay Viterbi plus 1 symbols here, convert them into decimal symbol. Please make sure that you perform this operation for these integer indexes. Yes, integer indexes, not that these values in a massive or array, but in the indexes that are addresses of this value. Yes. And accordingly, once you do this, you now have the received binary sequence and the original binary sequence that was intended to be transmitted. Now you can actually calculate the difference by adding up any mismatches. Yes, so we use the logical operation not equal to check if they are the same. Yes, if they are not the same, then well, it produces 1, and each one is going to count as an error, so we add all together these ones and divide by the length of this binary Rx vector to produce the estimate of error probability. So with this added in together, we now have successfully solved the part A of this task 3 Viterbi nonlinear equalizer. Yes. So let's double check first. Do we need to do anything about here? So it sets to 0. It sets to 0. It will stop here, but it's fine. Let me just set it also equal to 0 for now. Also equal to 0 for now, just so that program doesn't stop. Yes. And yes, and we also need to plot the results at the end here. So x-axis is going to be SNR and y-axis is going to be our BER Viterbi. So I don't know why there is double T. It shouldn't be. Yes, Viterbi. Now you may want to pick some color or symbols. I'm going to use red color and mark each point with additional cross. Yes. Like these. So some Viterbi results will be displayed here. Now I'm not sure if I need to specify something here. Actually, I can simply command them for now. Yes, and accordingly, let's see how it works. So if we run this program, oh, it's not a MATLAB, we have small error with this len here is undefined. It's because I have specified it here. In my case, in this new program, it's called n delay Viterbi. Yes. Since I'm copying from some of my prepared previously programs, some variables may have different names, which I may not be aware of. So this was a small error for me because I copied. If you have written correctly, you shouldn't get this error. Yes. So if we run it now, you can see that it will go through all the SNR. It shows some progress with these dots, how fast it's working. Well, for power of 4 it's quite fast. Impulse response is also very short, so this works good. And here we have some results. Yes, this is a bit error ratio of this Viterbi algorithm. Now if we increase this number to 5, it will start working slower. Yes, not much slower, but slower. And each time you increase this number, it will be slower, slower and slower. Yes. Well, actually, let it now run while we add the theoretical BER curve. So theoretical BER curve can be calculated according to this formula available at this document. Yes, so this document lists error probability for different modulation types: binary phase shift keying, quaternary phase shift keying, PSK, and final MCAM. This is the symbol error probability, this is the bit error probability. So we are going to use this formula. This gamma is none other than bit error ratio, or sorry, bit energy divided by the noise spectral power density, so that we have this parameter already. Yes, the Q function is a statistical function, more specifically tail distribution function of standard normal process. You can read about it more in the Wikipedia, for example, or any learning book on statistics, yes. But what matters for us is that in MATLAB we have a function called ERF, error function, and ERFC, complementary error function. And this Q function can be expressed via the ERF functions, yes. So if we want to calculate this Q function, then we would need to use ERF function otherwise, yes. So we may already actually type that in, that what we want to do is 0.5 multiplied by RFC, complement error function, of the alpha divided by square root of 2. So this would produce the estimates. Yes. So here you can see a simple ERF function. Here I used ERFC. Basically ERF and ERFC are related as follows. 1 minus ERF of alpha is actually ERFC alpha, yes. If we open the brackets here, yes, and add 1 minus, yes, then you would produce the same result as here. So now we need to take care of this alpha value parameter for the entire vector of signal to noise ratios, yes. So let's see how our alpha is organized, yes. So the alpha, and in additional, by the way, it's not sufficient to have this Q function, we also need to have this 4 divided by the num m bits, yes, which is log 2 of 16, which we already have calculated here, yes. So we already have it calculated, no need to calculate the same thing over and over, so we add this factor 2. So for the alpha, that is what is inside the brackets of this expression, yes. So that is the square root of the bit energy divided by the noise spectral power density, which we have as this variable already, yes. It is a vector of multiple values, so be sure we actually don't need to make any scalar works here. However, wait a minute, I'm not sure it's correct formula. Maybe I have made a small mistake. Yes, I have. We have to add multiply 3 here as well, yes. In this formula I will fix that, yes, in the final presentation that I will upload for you. But here we also need to add 3 times, yes. So that is my mistake. So that would be 3 multiplied by these and multiplied by, again, m bits divided by m minus 1. So we need to make sure all the brackets have been taken care of. So we calculate the argument, we calculate the Q function, and there we have the theoretical bit error ratio, which we plot here additionally, yes, by using the same signal to noise ratio, yes, and line style will be the line with the asterisks, yes. So the theoretical results will be additional line on this plot. So by now I believe it should have completed the calculations. Now you can see this line is a little bit more smooth. Yes, still it's not far away. But what we want to do now is to add to this picture this theoretical. For this we could run this script entirely again, but it's not really necessary, as we can run this part of code specifically once more, run selection, and it will mbits undefined, so that is because I have typed it incorrectly. Here we need a capital B. Run selection. Yes. So now you can see the blue line is the theoretical limit how ideal channel would perform, and you can see that our Whittleby algorithm has been really close to this. Yes, really close to this. Well, but this happens because in this function we are actually considering the history of the paths over the all duration. So that means if we have 1 million symbols, yes, so I am keeping the weights or metrics for each of these 1 million symbols for each of the states and use them to make a decision. Normally we would truncate this somewhere and store only part of this history, which may affect a little bit results, but nonetheless it works fast enough, yes, to actually for this specific value to store this history. So I decided why not use the complete history since we can, because we don't really worry about performance in this practical exercise. Yes, in real world, of course, everything has to be considered very carefully, but for this training exercise, yes, we want to get as best result as possible, and it's only if we consider all the history. Still, yes, as you can see, this is not so good result because we have too small number of symbols. Yes, we need to send more symbols to be reliable. Of course, the Whittleby result cannot be better than ideal theoretical results. This that it goes below this line is just a matter of randomness. Yes, it happened so that less errors occurred in this short time span that statistically should be, which is completely possible, yes, for random processes. But if we would have longer random processes, this line would stay from this line over the more or less same distance. Yes, it would not cross it, and it would not even completely merge with it. Yes, so this is only because we have limited number of experiments, and this is assuming that we run infinite amount of symbols, which we may never do. So if you happen to have MATLAB with a toolbox of telecommunications, you may use the MLSE EQ instead of the my provided function. Yes, for this function you would still need to provide your signal part, the impulse response in different order than in my function still. Also the constellation of symbols. Yes, since now I am separating the real part and imaginary part, I only need to specify PAM4 modulation symbols. Yes, the traceback length history. Yes, now it's not necessary to multiply by 10. Yes, this was just one of my experiments, and the parameter of RST. Yes, there is also continuous parameter. In that case you would need to take care of delay maybe. Yes, I'm not sure, but in this particular case, as you can see, receive data is already formatted in the same way as your A data, so no problems. And if I run this program, you will see the difference in the performance, yes, in MATLAB between my function and the MATLAB built-in function. So my function calculates, yes, you can see real part, imaginary part, the built-in function does it instantly, almost instantly, yes. Well, and take notice that this is actually for 1 power of 6. So you may see that actually even my function on the real MATLAB works faster than in Octave, just because it's more computationally effective, yes. And as for the MLC equalizer, this is actually a compiled C library, yes, and as you know, the compiled C library works a lot faster than MATLAB code, yes. True, it is possible to do so in Octave as well, to compile, however, that will require from you installing the additional libraries, maybe even trying to compile it yourself, and all the time loss wouldn't really be worth it, considering that simulation runs only a few minutes, yes. So if you have MATLAB, you may use this MLC EQ, which produces exactly the same results as you will see now. If you don't, well, it's fine. You can use Octave with function I have provided, and it will be more or less the same. Well, actually, I don't think we should wait, because I have this picture saved. Here you can see the Octave results in blue dots, the MATLAB results in red line. They match completely, and theory. They are both, well, more or less the same. Still, it doesn't hurt, let it finish. So let's return to our Octave code. So far we have done the Viterbi part. Yes, we now need to introduce also MSE equalizer as well. Yes, so for this matter we are going to use MSE eq function. So basically it will produce this equalized impulse response, yes, with these functions here and here. Now, for the symbols that we have received from the channel, we need to use the same as in the Viterbi, obviously for the real part and for the imaginary part. Now, this part of the code is in our code, let me double check, named a small. This is CAM symbols, yes, without noise, without distortions, without anything. So here you can see strange results. I believe that is actually why I was putting there this length here. So if you have MATLAB, you may need to actually experiment a little bit with this traceback length. Yes. So actually, let's try it. We're putting it back, run it once more while we work on MSE, just to see if it helps. So okay, I will also minimize this to make less effects on the screen right now. So this is our perfect symbols, which we need to train our equalizer. Yes, so that is also real part of A and imaginary part of A. Now we also need to know the length of the impulse response for equalizer, which is specified as 45, and I believe impulse response, yes, because delay can be calculated from the impulse response. So now what we need to do is to actually prepare this function based on this code fragment, yes, which we already did. So actually there is no need for us anymore to introduce both real part and imaginary part. It will work with the SR key directly as it goes, yes. So first of all, what we need to do is to evaluate this half of the impulse response, the delay, yes. So I'm going to, and actually also beta parameter we need as well. So I'm going to copy them both in my function. So preparation. So we find the delay, we specify the beta parameter for this function, and next what we are going to do, we need to find some additional parameters, such as the length of the channel impulse response. Yes, so how long is our channel impulse response? And well, I'm not sure, do we even use that anywhere? Well, actually we don't even use that anywhere in this code, but let it stay. And also let us evaluate the number of symbols. So number of received symbols. We are going to need that for the effect of adding these output, so that you don't get confused, is your program working or not, is everything okay, so you will see that it plots one dot at a time, so you know that it actually works. Yes, as you can see, now after I increased this delay for the equalizer, it now matches completely with my result. So I'm not exactly sure if that delay is the same for the Viterbi algorithm in MATLAB as in my implementation. So just be sure that if you use MLSE-EQ, you take care of this delay parameter to get good results. Yes. So for now, we are going to close to remove no to return to Octave. Yes, and continue working on this function. So now we can actually start calculating the equalizer, and this is where we specify this. Yes, so initial values, well, basically what we can do is to copy all of these. Yes, we don't need to do that, so we copy all of these and start removing the unnecessary parts. Yes, well, first of all, we only have real part, we don't have imaginary, so let's name it simply as HEQ, which is our output of this function, and we fill it in with zeros corresponding to the length of your equalizer. Next step, this is not actually autocorrelation, well, calculate iterations of MSE equalizer. Again, we don't have imaginary part, so we remove that altogether. Signal fragment vector, it's a fragment of the signal of length LEQ. Now what we need to make sure that we remove any occurrence of the real part. Yes, a real removed, a real removed, real removed, removed, removed here as well, here as well. Well, actually, this also doesn't need to be. It is already a real number, so it won't hurt, but it's unnecessary operation, yes? So, I suppose I have made all the corrections. Just to be sure, I'm going to simply copy it from my already working code, so that we don't spend any time on unnecessary mistakes on my part here. Finally, if we want to add this effect of plotting these, yes, let us go to the Viterbi function and find this part. Yes, so it outputs 1 dot per 1/50th part of the total symbol. So if the current symbol is divisible by 50, we do plot dot, otherwise we do nothing. Yes, so we are going to add this just for visuals. Yes, and in order for this function to start a new line, also don't forget to add this printf at the end as a new line beginning. Yes, so this function now will calculate these equalizer parameters. So I might even try and run it now just to see if it works. Oh, of course, I don't know what is k in this function, and let's go see why it's not working. Because it's not k, it's I in this for loop. Yes, so now I need to do that. Let's try it once more. Yes, as you can see now, it actually still takes some time, comparable time with the Viterbi algorithm, I'd say, in Octave at least, but it's working. Yes. So this function is prepared. We now may close it and forget about it. This also may forget about it, and let's return to this part. Yes, as you can see, now we need to apply this equalizer to each real part and imaginary part of the received signal. So again, you may use this code in this method to see how it was done, to remember. Yes, because we already did that. Yes, so apply equalizers. Yes, as you can see here, apply delay, and so on and so on. So I'm just going to add lines of the codes here by using my conditions of the second screen. So the real part as a filter for equalize the real part and the real part of the received signal, and the same way imaginary part. Filter equalizers imaginary part impulse response and imaginary part of the received symbols. Now we merge them together in the QK symbols. I specifically use the same notation as in the previous practical exercise, which is not similar to what is here. We could have called it also as received data, but better to have access to all of this data. So if you could call this received data, you would lose this data, which may not what you want. Yeah, so I decided to have a different name for this variable. Now, you also need to apply the delay caused by this equalizers filter. This is n delay MSE. Yes, we started from the beginning, and for the comparison purpose, you also want to apply the same delay to these symbols. Yes, but from the other end, from the end of this array. Yes, so we add this delay at the end. Yes, and start from the first symbol reading to end minus this symbol. So in total we lose from our 100 thousandths, yes, or whatever was that, from this number, we lose this number of symbols. But it's fine, it's just necessary to correctly evaluate bit error ratio by making division accordingly. So finally, we want to demodulate. So again, we use the same approach as here. We calculate the binary data, we calculate the binary received data, we calculate the binary perfect data, yes, from this SimK, which we already have delayed, so no need to add delay anymore here, because this delay was already done here. We could have simply typed like this also, but this is easier to see, yes. And finally, what we want to do is to calculate this error probability, error rate, yes, by comparing again received binary with the original binary and dividing by the length of the received. So if we run this program now, it should calculate both Viterbi algorithm and minimum squared error equalizer. However, I haven't plotted these results, so let us do this now. Let's use, say, blue color for these. Yes. And also let's put this to 1 power of 4.